All right, we're in video 2 of class 7, and we're in section 4.6 of Sengel. Here's a slide that comes along with the textbook, so I'm not taking credit for that, right? Mathy stuff. Okay, here we go. So the big idea is there's the different approaches, the system approach and the control volume approach. And we want to try to link those things together. And it's Reynolds transport theorem that really does that linking for us. So here is Reynolds transport theorem written here at the top. I don't know. I think I'm going to do that later in my notes. So let's take a look at my notes here. I wrote them, so we might as well use. So the system description, as we had mentioned before, is Lagrangian perspective. And well, we take a look at a collection of mass, and we follow that collection of mass, right? And follow it. So we see what happens to the thing. But here, the control volume perspective, which is what we prefer in fluids, is Eulerian. And we focus on a region instead. And we watch as stuff flows through it. And that region doesn't necessarily have to be stationary, but it can. It's made up of a region made up of control surfaces, right? So we have surfaces in which not all control surfaces necessarily will stuff pass through, but we will have things passing through there. And our main concern is the velocity as they pass through, and we'll see that. What's awesome drawn is like at any instant, this entire thing, let's say at an instant in time, let's go at t equals 0, the system, at least in the one we drew, the system and control volume are the same thing. But if we have a little bit of time, right, this thing is going to keep, this mass is going to move, and so now all of a sudden it has come out slightly out of our system. So here is our control volume, but here is the mass at state 1, and then here is the part of it that's come out at state 2, right? So we write that the system is, which is the entirety of the mass, is the control volume minus what leaves after, this mass has left in that region, but now we have to include the stuff that has come out of the control volume. I guess just leave it at that. Yeah. So like here's what we've just drawn is sort of like a fixed control surface and control volume, and now you can see this is the control volume surface of the stuff coming in and out, where the gray stuff here is the mass, right? So this is the system. Whereas, okay, so we could have a moving control surface, like for instance a jet engine, and so you could see where the control surface is. We might draw them a little ways away because spoiler alert, a jet will actually influence the fluid in front of the jet for at least a small amount of distance, or it can be fairly substantial. So we want to make the control surface actually larger than the jet itself, so it can capture that. But you can see that the system will at time 1 be inside there. At system 2, it'll go flying out later some other place, right? So it was in here, but this control surfaces and the control volume is actually moving, right? So we have to consider that. And you might even have deforming control surfaces like the balloon. It might change shape as mass is leaving it. And as we mentioned, that Reynolds transport theorem is the thing that connects these two, and restated right there. So what is Reynolds transport theorem? Well, first we start out with what we're looking at can be a generic thing that sometimes we'll call stuff. At least that's what I like to think of it. And it's capital B stuff. But sometimes we want to do stuff on a per mass basis, very common. So we'll go stuff divided by mass, because it's the mass that is the thing that's transporting stuff. It is the transport in Reynolds transport theorem. So if we're going to take this system description right here and find out how it's changing with time. We want to do what is essentially the material derivative of the thing. That's why we brought up the material derivative. We could take the partial derivative of B, and that's just the stuff that's within the control volume and how it changes with time. So that the time rate of change of the stuff in there. So like from the previous diagrams, when we were looking and we're saying, hey, this stuff is leaving and coming out, or entering this mass and leaving, well, that's going to be the time rate change of the stuff in the control of the control volume. Let me take that out. This is the control volume changing shape, right? So it might accumulate or it might deteriorate, right? The quantity of it. So a lot of times it's going to be changing shape. Maybe I'll say that's a better one. Here is the stuff coming out, and it's by convention it's positive, whereas the time rate change of the stuff coming in is going to be right here. And this is quite often something we might want to associate maybe with the. I think I can say that. Yeah, I can kind of say that the convective portion of the thing. So this is sort of an accounting. And as I mentioned, a lot of times we want to know the stuff per mass because it's mass that's moving the thing in and out. And so we can rewrite this part, the control volume. This is the control volume changing shape or the quantity or accumulating of stuff in and out of the Colosseum, as the analogy went, Dr. Foley's analogy. But right here, we could say, well, mass out, and this is going to be mass flow times B, right? So B out minus the mass flow in, and this is B in, right? And so these are equivalent up here because it's the mass that's transporting. So the mass flow, the time rate change of mass, right? And these are in like kilograms per second or slugs per minute or whatever. It's just going to be a mass per time type of flow. And this is a quality or of the fluids that are taking place here. And then like we might want to also replace this because sometimes we're going to have we're going to think in terms of the density and the volume that's going to happen to the thing, and we want to relate it to the velocity, right? So we could rewrite this first part, but now rewrite this other part right here as saying the density at state 2 times the area of state 2 times the velocity of state 2 times the parameter that we're transporting. And same thing here for 1, right? And recognize what has happened here is that this right here is the mass flow out, and here is the mass flow in. And they are transporting this stuff. These right here are the chariots, and here's the gladiators that are coming in and out of the Colosseum. Noteworthy that this velocity right here needs to be perpendicular to this area for this thing to be true. And so in terms of vectors, what we want to make sure, so this mass flow is crossing control surfaces. So in order to get the signs correct right here, you see that minus is in, plus is out. We draw outward normal unit vectors to control surfaces. So you could see if this is the inside of the control surface, right, and inside of the control volume, and this is the control surface, this is the outward normal. And if this is, so now here's the outside of the control volume and the control surface on which it passes, and here's also an outward normal where this is perpendicular to the surface, and just says that is perpendicular to the surface. So you might have velocity coming in at an angle, but this dot product means that it's only the part of that velocity, the component of the velocity that's normal, perpendicular to the surface that counts. It also ensures that the positive and negative are stood up correctly, right? Because when the velocity is coming in, it's going opposite direction of that outward normal, which means it'll be negative. But when they agree with each other, it will be positive. And just a few more things in here in terms of the stuff. It's sort of it's a little tough conceptually at first until you see this list of what the stuff is. But I think I'm going to rewrite this out right here, where we have this is what's taking place in the control volume and how the control volume is changing. So if the control volume changes with time, this is what we use. And if we have the things coming in and out of the control surface, we'll put the B, that's the stuff getting transported, density right here, and we'll have the velocity dotted with that outward normal times, and we're taking the integral across all of the control surfaces. So sometimes I'll even put a circle right here. I'm not sure if that's appropriate now at this point, but that just means that we're going to go around everything right here. And that, as I mentioned, that dot decides positive and negative. So for a fixed non-deforming, right? So a fixed non-deforming control volume, this part goes away. And all we're left with is, okay, so if it's fixed and it's non-deforming, mass might come in and leave. So we still have, I think this is a partial derivative with respect to time, the integral on the control volume of the B that's inside there times the density times the incremental volumes, right? So little tiny volumes. And then we're just going to repeat the stuff up above. And this is sort of an important equation. If you remember Green's theorem, or I think it's Gauss theorem, Green's theorem, I'm trying to remember. And we're about to get a visitor here from the janitor lady. So anyway, this is an equation right here. It's an important equation where it really makes a connection between a control volume and a control surface right here. And so finally, I think we'll be done with this video here in a second. Examples of stuff, we've been waiting for this. One of the hardest ones conceptually, I think, is the very first one where we take mass, because we're using mass as the transport, but we can use Reynolds transport theorem to describe mass, where B is the stuff, so it's mass, but then of course mass per mass is just one, and we can use the conservation of mass. That same idea for volume, that could be the B, that could be the stuff, and so that volume per mass is the specific volume, right? AKA 1 over the density. And if there's no compressibility, if it's incompressible, this will hold true, and we can have the conservation of volume flow rate if it's incompressible. And we could also have linear momentum, could be this stuff. So mass times velocity, and then of course the B is just the velocity. And this is actually where Newton's second law. We're going to do this later in chapter 6. We're going to take this, and we also have internal energy, and we're going to see soon that this can help us to get towards Bernoulli, right? So this Reynolds transport theorem is conceptual, and here's the stuff that we're transporting, and I think that's enough for one video here. Hopefully it didn't make it more confusing, it made it less.